Thanks, Suranga. First, before I start to share my talk, or my slides, actually, thanks to all who organized that. I mean, were great speakers, but I hope if I now would see your bio signals, I hope they're also slowly calming down because you realize it was a big success because I'm the last speaker and everything worked so far. So hey, thanks team and Suranga for organizing that. With that said, let me share my slides and my talk. And actually, can you see my slides or you see my moderator slides?
Oh, we see your full slides.
Perfect. So yeah, so again, thanks for organizing and for inviting me. And as the last talker, I just want to talk a bit about what my research is and how it fits into that general symposium of assistive augmentations. And assistive technologies. So basically, I'm originally coming from the field of augmented reality. And I actually, one of my first supervisors, he always came and said, if it's not visual and if I don't see an image, it's not sexy. So I'm slightly biased because of that. I think all the stuff that I have seen today is sexy, but somehow I'm stuck in it, that it has to be something visual. So today I will talk about one of my field, which is, I just summarize of computational classes and actually the kind of teaser image says. So actually what I'm trying to do with my background in augmented reality is I want to take some of the technologies and just want to see how the future of classes might look like, because I think the future of classes is that they're computerized so that we can enhance our vision, but that we can also compensate visual impairments that we can't compensate with purely optical solutions. But before I go into that, I just have to misuse that session a bit. But actually also saying that we organize the IEEE VR, so one of the biggest, or the biggest VR conference next year here in New Zealand. The journal track is over, but I have seen many of your talks and that have relation to VR, and that was also emphasized. So there are still several tracks, including the conference track, which is open for submission. So just as a hint. But now back to topic. So I already indicate, so what we want to do on or one of the research direction, what I'm working on is the idea of your computational classes. So why is that? I'm wearing glasses, many people wear glasses, and it's interesting because if we think about classes, and assistive technology, it's a widely accepted assistive technology. Some people wear window glasses because they think they look smarter or they look fashionable, but it certainly is something that we are absolutely used. Not only because we use them for centuries, and this is what you can see on the left-hand side, so we used glasses for centuries, but they're proven to help and there are actually almost no problems. Still, I think there are certain limits, and this is classes are also for centuries, not just similar in form factor, but also in their basic mechanics. And this is, they use some optics that are made to a specification for you at a specific point in time. And after that, they don't change, okay? So one of the idea is that we, as indicated before, that we want to replace these static optical elements with actually computerized technology. And there are different ways on how you can do that. And I want to briefly talk about two of the things that we try. And one of this is that we have computational optics. So the idea is that we replace the static or otherwise static optics with computer-driven optics that can be made adaptive and that also can do things that normal classical optics cannot do. And the other direction is that we use technologies from augmented reality displays, so optical see-through head-mounted displays. And what I mean with that is that we integrate, for example, small half-transparent displays into your classes that again can be used, for example, to enhance your vision, to give you superhuman vision, or to helps us to compensate, for example, certain visual impairments. And there are a lot of visual impairments that are out there that cannot be easily compensated, some not at all, some require surgeries and so on. Okay, and this is what I want to talk about today. And I want to talk initially about some of our works that is a collaboration with Japan on computational optics. So the first project is that, so basically compensating refractive errors of the eye using computational optics. So I have seen the pictures, many of you wear glasses as well. So for those of you who are lucky to not wear glasses, so what's the problem? many of us, an increasing number, have refractive errors. So what is it? The problem is usually in the anatomy and the muscles of our eye. So basically, light rays can't really focus within our eye. So it depends. Some of us have problems with distant objects. Some have problems with close objects. Unfortunately, many of us will later have the problems with both. But what works is we can correct them by putting additional optics like normal glasses in front of our eye. Okay, and that helps our eye to refocus or correctly focus the light. And that works. So on the right-hand side, we see you have either glasses that, for example, help us to read the book, or you have glasses that help us with the distance. And again, there are also classes, bilinear classes, for example, that help us to see both. And what I also said, they work with the static lens. So what we tried to do is we replaced this lens with programmable optics, so dynamic optics. And in a specific work, which is a collaboration with Yuta Ito's group, who was and still is at Tokyo Tech, but also now changed over to University of Tokyo, is to replace this with phase spatial light modulators. So thinking a bit about it, it has a bit like a display, but there is no light source. And depending on what you render on that kind of display is you can simulate lens. So you see, you basically render a specific pattern. This is what you see on the right-hand side. And that allows you to render or create lenses. And of course, you can re-render them or change them. And that allows you to do something like this. So actually, what you see there is that you see actually an adaptable focus or focus tunable lens. So we can actually build a lens that is focusing on the foreground or the background. There are different approaches to do that. So ours is not the first, but we come in a second. Ours has a couple of advantages. But with the first thing, again, we can help you or your eye to focus on objects. So there's a really, really cool work that I just want to mention from Gordon Wettstein's group in Stanford that used a similar technology, or they used a similar idea. So they built these classes, so they're called autofocals. They use different versions of focus tunable lenses, but what they do is actually what you show in this video. They track actually your eyes and they track on what you focus on, and they focus for you. So actually your eye can be almost totally lazy. You focus on a distant object, and that device will adjust the lens accordingly. They will measure the distance. They have the depth camera on top. We measure the distance and will figure out on what distance you need to focus the lenses to support the wearer. Yeah. What we can do, our prototype that we built is not that mobile, but we can do more than that. What we can do is actually we can also do multifocus. And that is something that for certain refractive errors, it would be really beneficial. So what we can actually do something like this, we cannot just like Gordon's group focus on the background or on the foreground, but not both at the same time. So with our approach, what we introduced, we can do something like this. So we can, for example, if you see no modulation, there's an object in the foreground and one in the background, we can create or simulate a lens or render, so to say, dynamic lens for far focus, and then the distant objects are in focus, or for near focus. But we actually can also render or create a computational generated lens that puts both in focus. Yeah. So if you struggle, for example, with bifocal glasses, many people switch because of that, we can really give something that puts both in focus, which you normally can't do. Okay, that is I have to say, I forgot to put actually picture here. So the current prototype is not really mobile. So that is more an approach that is really more on the optical bench level that we experiment that, and the results are a bit more qualitative. So we haven't done a full user studies, and you see there also still some optical imperfections, but it's doable, and we think there's more like this coming. And we're working on that so that we use other computational optics to correct, for example, the certain things of refractive errors. But the other thing, what we want to do, or what we do, and I want to talk a bit more about, is actually going away from computational optics, but actually using half-transparent displays that we normally use in augmented reality for compensating certain visual impairments or enhance our vision. And there I want to talk about two projects, one a bit more detailed and the other more briefly, because it's in a different stage. So the first is the project we were actually doing for, I think, like 3-4 years. And this is about compensating color vision deficiency. And we just wrapped up that project, so it's just all done. But I still want to talk you through a bit. So the general idea is that we picked a specific problem of visual impairment, and this is color vision deficiency. So most of you know it under the name of color blindness. So there are very different forms of that. So basically, and it's usually male. So the problem is that they can't distinguish certain colors. We picked that problem out of that many interesting problems that exist because it has several advantages. First of all, it's extremely well understood what's going on. Next thing is there are a lot of works actually in the field of HCI that created interfaces, web interfaces, mobile interfaces that you can see here that help people to deal with color vision deficiency. And I know, for example, Suranga was also active in this field with a very different wearable approach, which is actually also very cool. I should have put it in here. So our idea is that we want to compensate it with something similar to classes. I already said that there are different forms. I will not go into detail. I will just say, depending on your severity, you can be actually quite impaired in your everyday life. So just as an example, I have an extremely talented PhD student working on that, Jonathan Sutton. You will see him in several images. He is colorblind. He couldn't do his job that he wanted to do, which was good for me. So he did a PhD, but he couldn't do his original job or fulfill his original career dream because he was colorblind. So, and again, there are many or several examples of that, of areas where you can't work. So the general idea, again, on a very high level, we started with traditional optical see-through head-mounted displays used for augmented reality. We're actually quite heavily modifying them because what we actually wanted to do, or what is needed for our approach, is that we have a camera that is seeing the world as your eye would see it. And it's normally not the case because normally the cameras are a bit further away from actually your eye. So we corrected it by virtually placing a camera via a beam splitter very close to your eye. And that allows us to actually receive a camera image that is very good approximation of how you see the world, or how that specific eye is seeing the world. We can now take this camera image, we can do some real-time computation on that. And actually what we do is, and this is what you see on the left-hand side, we compute what we call an error image. This is the information that people who are affected by color vision deficiency would miss out on. So if you're colorblind, for example, in that specific Ishihara marker, you would not see the 6, but you would not see anything. Yeah, and in particular, if it had a severe form. And now what we do is we create a visual overlay. We first compute it, and then we display that visual overlay that exactly as seen by your eye merges with the background and slightly shifts the colors towards the frequency that you can again perceive and distinguish, because usually the biggest problem is distinguishing them. Okay, in detail, it's not that easy, but it's Friday for most of you and it's relatively late, so I spare you the details. But we built a lot of prototypes for that. We played with different classes. We ran different studies that required different prototypes. So we had optical bench prototypes, we had very stationary lab prototypes, and we had mobile prototypes, and we just had actually a follow-up of our original work accepted to Tokai, which gives a very good overview about all the prototypes and all the approaches that we developed throughout this larger project. But just to show you in the video, this is one of our older prototypes, how it looked like. That was a stationary one. And if I move my camera roughly there, it's not calibrated for the camera, but for me here, then you see roughly an overlay. In fact, I have to say, here's some other images for calibrated camera. What actually in many of the image, what is maybe distorting is the fact that it's showing a very strong effect. And usually we do that because we had often people who came to the lab and received the demo. And we said, oh, this effect is very strong. And this is what you see on the right-hand side, because otherwise they would not see the effect at all. Because most of the people, for example, who are affected by color vision deficiency, they would need a very subtle modification. So they would see something that we see in the middle. Yeah, so, and you would probably agree that the change from the left to the middle is really minor, but that makes a big difference from seeing a 22. This is what you would see if you're colorblind, to seeing a 74. And usually we just show this very extreme change to make it really clear that there is a difference. But we also evaluated it with more mature material. And here just a couple of anecdotes that came out of some of the several studies. So we ran over 5 studies with that that came out. So for example, we had one participant who said he struggles the most with actually computer games. And that's what you see on the left-hand side, because he said he has a big disadvantage because he cannot see really the health bars if they're red or if they're green, which gives him an advantage, a disadvantage in a fast-paced game. So we try to correct that. And here, this is something that is captured through our classes. And so again, we kind of wrapped that up, that research on color vision deficiency, even though we did it for years. And I just want to give you a kind of outlook on something that we do now. So we still follow that idea of building classes that modulate the world. So I would not consider it traditional augmented reality because we don't add 3D information and so on. We really just modulate how the world looks to the wearer. And one thing that we are currently acting or quite active is guiding attention. So in particular, I hope you see that here. So that is actually a video which should switch back from modulated to unmodulated. So it's actually an image. And if it's modulated, what we actually do, we change via classes the saliency of that image and actually emphasize that silver car. So it's a very subtle way of actually guiding your attention. And this is known in psychology, and there are lots of studies on that. Normally with video material, so they change the video. What we do is we don't change images or we don't change video material. We change how you perceive the real world. Yeah. So basically, again, on a very high level, it's relatively similar, and detail is quite different. Again, we build some classes that capture the world. For example, here that forest scene. And we compensate, we analyze the image material, and we computed an image which looks very weird. But actually, when we display that weird image in the classes, it actually changed the saliency of the scene. So here, this is highly emphasized so that even through zoom compression, it might still work. So the general idea is we blur a bit the rest of the world. We reduce a bit the colors, so it's all a bit numb. And certain image areas, they just look more vivid. They have a higher contrast and they have more colors. And we ran a lot of studies on that and showed that, for example, it attracts your visual attention, that you look there quicker than, for example, compared to without this change. So basically just an idea so that you believe me, it's working system. So I'm not sure how clear it is here. Again, this is not properly calibrated because I just moved the camera right there. But even for this one, the general idea is that we, for example, similar to augmented reality application, we could tell you in a very subtle way, look there or pay attention. But also you can think about this very differently. You can actually think about it as noise cancellation for your eyes. So many of us, we have now these headphones, and we use noise cancellation to shield us away from the world. So let's take this example, and this one I just made up in Photoshop quickly, so unlike the others. So let's say, for example, I want to work, I'm sitting at a busy place, I'm easily to distract. So what I now can think, I put on the glasses and actually change the saliency of the real world, tone it down so that it's less visually distracting to me, and then I focus more, for example, on my screen. And for this part, then, for example, I increase the visual saliency. Yeah. So this is something that we're currently working on and have quite promising results. To wrap this up a bit, so I hope in these few minutes that I shared with you a bit my passion on really rethinking how classes should look like and how they are driven, how they function. And I think there are, of course, many opportunities and applications for that. Of course, I talked a bit about vision impairments, and there are a lot of vision impairments that could benefit from approaches like this. There's reading support, for example, if you think about dyslexia. There's also prevention of certain visual errors that might arise. So we had actually this document where we went through all brainstorming and all the things what we can do, and we just started there. Of course, we can also think about superhuman vision, and Albrecht this morning talked about human AI integration and about increasing the bandwidth. And actually our eyes, they are among the sensors in our body with the highest bandwidth. So I think they are also a very good starting point. A last point that I would say, and this is more anecdotal and it's almost more a question to all of you. Something we all work on emerging technologies. And I think a problem that we all have is the problem about accepting this technology. So something that I observed but it's just my observation, is if we use a technology and use it for people that have a certain impairment or deficit, technology is way more accepted than utilizing exactly the same technology to enhance us. Yeah, so that is just my feeling. That's my observation with my student. Usually I show them something like this. So many of you might, or some of you might know the SenseCam project, this relatively old, really cool project. So just in a nutshell, this is actually a neck-worn camera that is always on, okay? And everyone I show this project, so this is actually to support people from dementia or affected by dementia. Everyone I show the project, they love it. They absolutely love it. However, if you now think about the camera that is always on, like in the Google Glass that is capturing, there's this, of course, there are big concerns there. So this is just as an example that depending on how we use the technology, it might be perceived very different. And maybe it's also something, if you run into this problem, maybe also think about your technology, how it can be used actually for people who would actually really benefit from it because they have specific needs or specific impairments, okay? But it's more something that I would put up for discussion, and maybe you think about it very different. So my last comment is just thanks to all my colleagues and students, particularly Jonathan Stratton and Matthew Cook, who worked with me on that, but also Yuta Ito from Tokyo Tech, who's collaborating with me on those topics. So again, thanks for the invitation. I think it was a great symposium. I'm now open for questions, and I will end my slides.